Okay, so we're talking about trig. We're done with logs for a while. I think the last logs test didn't go so hot for some of you, and we're probably going to kind of review that over the course of the next few weeks and months with an occasional like problem of review, just to try to keep you up to date with logs, because you do need to know some logs in calc where you're going next. But this, when I asked kids that were in calc, this was the #1 topic that they said, make sure they really know trig, because it comes up a lot in calc. Okay, so let's make sure that you know trig. Let's go back to what you remember about from the past. There was one saying that sounded like an old Indian talking. Sokatoa. Would you please write that on your paper? Sokatoa. Show me later. Right now, just get your notes up. SOHCAHTOA. Sokatoa. And what does the S in Sokatoa stand for? Sine. And the OH? Opposite over hypotenuse. Ka. What does that stand for? Cosine, and that's? Adjacent over hypotenuse. Very good. Sine, oh wait, I should write it SOH. And TOA, tangent, is opposite over adjacent. Okay, so those, you remember those. Okay, so what are these opposites, adjacents, all those kinds of things? Well, from an angle's perspective, like that angle, there are angles that are adjacent to it and opposite from it. The angles that are adjacent to it is, adjacent means right next door. So this is the adjacent right here, angle, or sorry, adjacent side, and the opposite side's the one across from it. And then this is always the hypotenuse, no matter which angle you're looking at, no matter which perspective you're coming from, that's the hypotenuse. What I mean is, like, if we change to a different angle, like maybe over here, and look from this angle's perspective, that's still the hypotenuse, but that's not the opposite side, or sorry, it's not the adjacent, it's now the opposite side. See what I'm saying? So those two could flip around, adjacent or opposite, depends on which angle you're talking about, but the hypotenuse stays constant. All right, so when do we use trig? Well, you use trig on things like this. Let's say we knew this was 30 degrees, and let's say that we knew this was a 7-foot tall triangle. You could figure out then how long either of the other two sides was just by those two pieces of information. Like you could figure out this side right here, for instance. Now, just think for a second. From that angle's perspective, should I be using tangent, sine, cosine? Which one has the opposite and the adjacent? Yeah, tangent's the one we'd use. So why don't you write this little sample triangle out for yourself and write tangent, because why? Because tangent of this angle, 30, is equal to the tan is TOA, which is opposite over adjacent, and the opposite is 7 over the adjacent. I don't know, so I put a question mark, so I'm going to put a variable. I'm going to call it x. And then this will be easy to solve, because you'd grab your calculator, you'd type in tangent 30, and you'd have a decimal, and then you just get solved for x, and it won't be a big deal. Okay. That's a really quick power review of what you do when you're solving simple tangent, sine, cosine kind of problems. Okay, do you remember this? Is that coming back a little bit? Okay, there were two really important kind of triangles. The 30, 60, 90. That's this one. 30, 60, 90. Remember what this one's called? 45, 45, 90. It is, two sides are equal, not necessarily all three. You could design it so all three were equal, but you wouldn't have to be. And if two sides are equal, it would be called isosceles. Good. And if all three happen to be equal, which they could be, then it would be equilateral. Okay. Very good. But they have to have two equal in this case. Know why? Because those angles are equal. So since this side here and is opposite from this side here, they have the same number of degrees opposite them, then they are the same. Do you remember this little thing where if this is x and this is x, then this side, yes, you could use a squared plus b squared equals c squared, but there's a fast way if you just have it memorized. X square root of 2. Very good. Okay. All right. And there's another one that's like that in the 3060. Do you remember that one? This one's x. This one's 2x, which is twice as long, because that makes sense. Smallest side, biggest side. And the last one, x square root of, it's not that complicated. Oh, yep, just, you're doing a different one. No, I know, I always thought that too. I mean, I get that confused, but you got to remember it this way. This is the longest side. This is the shortest side. So they're the ones that are going to be double each other. Okay? It's the hypotenuse is the one that's 2x. I know. That's the reason it seems like it should be, since this is 30 and this is 60, it seems like these should be the two sides here and here that are double each other, but they're not. Okay. So there's your quick reminder of trig you're supposed to know already. And here's some stuff that it is good to know about trig. It'll solve any of these kinds of problems. Rotations, that's about moving, right? Vibrations, that's about moving. It's like even the ground going up and down is kind of like a vibration. Except this is a vibration that is like constant, like maybe vibrating strings, for instance. That's like a tone that's being made by a string that's vibrating, like a harp string or like a piano string or like a guitar string. Those all can be studied based on trig. Rays of light, that's because, well, I don't want to get too complicated here, but things that have to do with motion seems to be a common theme here. All right. Some quick review about circles. Stay with me, please. Stay focused. Is there something that I need to know? Getting a random breeze. It's probably a ghost. Kid died in this room a while back. No, just making that up. Okay. Some quick review. Okay, this is a circle. Do you know what it's called when it's all the way around the circle? What's that called? Circumference. Next. A little red line there. What's that? Radius. If I doubled that, I'd go all the way across. Diameter. All right, so there's a whole bunch of words about circles that we have to know. Why? Because a lot of this stuff has to do with triangles and circles. You know, I just showed you the triangle stuff a second ago, and there's a lot of stuff that has to do with circles. Remember how I was telling you here how about rotations? Okay, that's like something that's going around and around and around in a circle. All right, and the way they define an angle is actually based on this ray moving and opening up, and the bigger it opens up, the bigger the angle is. So anyway, circles are crucial, so I just want to talk about that for a second. All right, do you remember that this little piece of the circle is called? It's like a wedge of pie. A sector. Good. And do you know what it's called? Just this piece on the end that's a curvy piece of circle. Starts with an A. AR. Arc. There you go. It's an arc. Okay. Let's talk about conversion. This is going to become important today. One of the main things I need to teach you is about converting. Converting, you're going to be learning to convert something into units that you've never even understood before. But let's start with converting something on something you do understand. So for instance, 65 miles per hour into feet per second. Please write this down. 65 miles. And miles per hour, per means divide, so you'd write this. Oh, wait. I know you can do this a fast way, but you need to understand what you're doing. This is a lot like what happens in science, where you have units that have to cancel right. Miles over 1 hour. Would you agree that that's a way to write 65 miles per hour? Okay. Then, if I wanted to change this into feet per second, if I multiply by the right thing, it will change it. But it won't change its amount, like its value. See, if I just times this by 2, I've totally changed what I had. I had 65, and then I'm going to go to 130. I don't want to times it by something that'll make it grow. I want to times it by something that'll keep it the same exact size, but change its units. So what can you multiply by that'll keep it the same size? You can multiply it by 1. Well, that seems stupid, but if you multiply by 1, meaning 5,280 feet, okay, over 1 mile, do you see how 1 mile is the same as 5,280 feet, and therefore it's 1? That's why you can do this. That's why you can multiply by 5,280 and not change what you had. Okay, so now cancels. Do you get what I just did there? Okay, would you please take your calculator, multiply that out, and just tell me what we get. I know it's not the final answer. 352,885 over 1. Is that wrong? 343,200. Thank you. Okay. Somebody had fat fingers for a second there. Okay. So this is, okay. We all make mistakes. Feet. All right, so that's how many feet per hour you're going. In case you're ever traveling at 65 miles an hour, you can always say, hey, Dad, you know we're going 343,200 feet per hour right now. It's true. I almost said per second, but I didn't. So now I'm going to change it to per second because, see, it's once per second. So I'm going to get rid of this stuff, and now I'm going to change this. It wasn't the ideal there. Okay. I want to change this now to seconds. So the way you should start thinking is this. What could I multiply it by that would make the feet cancel? Well, then obviously I need feet down here, right? That'll make the feet cancel. And if I want seconds to be left, I should put seconds here. All right? That's not going to work so nice. Hold on. I'm a little... You're right, I don't want feet to cancel. I was getting confused. I want the hours to cancel. Thank you. I was thinking right, but the good part is that after looking back at it, I could see I had done something wrong. What I'm thinking right in a couple of ways, but not completely. Okay, so here's the feet per second is what I should have left. I want feet left up here, right? And I want seconds down there. I do. I want seconds down there. Okay, just wait. So, would you agree that I want to put something in hours to make them cancel? Do you get that? And do you agree that I want seconds to be left? Okay, so I'm doing it right. Hours over seconds. So, what is the fact you know about hours and seconds? Excellent. 1 hour is 3,600 seconds. Now, if you didn't have that memorized, it's not that hard. Just take 60 times 60. That's a lot of seconds, isn't it? All right. Eye opener. So would you please take that, divide it by 3,600, and you get your final. Okay, give me, he doesn't need 2 people shooting insults at him from the back row. Okay, go ahead. Tell me the answer then. Good enough. Okay, and that is in FPS, feet per second. Okay, that's different. Okay, so now let's talk about, there are a few things that you're going to learn about over the next few days. Angular measure. You'll understand more about that tomorrow. Degrees and radians. You're going to learn a lot about that today. Circular arc length. You remember that little arc? We're going to learn how long that is. It's a simple little formula, piece of cake. But you're going to learn that tomorrow, actually. Angular and linear motion. Linear motion is just moving straight. Angular motion is like going around and around and around and around and around. So you're sort of moving, but you're sort of never going anywhere. That's angular motion is compared to linear. And why? Angles are the domain elements of the trig functions. As in, if you've got this like trig, there you're going like tangent of 30 is equal to 4/5 or whatever. That one part of that is the domain, and the other part's the range. We're going to talk more about which part is the domain and which part's the range. You'll find out more later. Right now, I'm focusing on understanding angles and radians and how to convert between degrees and radians. That's the main thing I have to make sure you get to. All right, so here's an official definition. Angle is determined by rotating a ray about its endpoint. I have made a ray here that I can rotate about its endpoint. Watch. And that didn't work at all. Hold on. Touch. There we go. Then I can make it rotate. See? And the farther I open this up, eventually I get to the end spot. The spot was called the terminal side. This is called the initial side, where it started. And if I open this up, eventually I get to this spot right here. And I've created the terminal side. And where these two separated from each other, this angle right here results. Okay? So the official definition of an angle is that it came from a ray being rotated about its endpoint. But you didn't know that. All right. The starting side is called the initial side. The ending is called the terminal side. And then the end point of the ray, that's like right down here, that's the vertex. Okay? All right. So now, determined by the amount of rotation from the initial side to the terminal side. In other words, how far did it rotate? How far did it open up? That's how big the angle is. This angle right in there, okay, you got to stop doing it. This angle right here is called the central angle of a circle. Okay? It's the, on the inside there, that's the central angle. The one whose vertex is the center of the circle. All right, we're going to do a lot with central angles. All right, there's 360 degrees in a circle, right? There are some really cool reasons why there's 360 degrees in a circle, which I'm not going to talk about today because I realized last hour I need to really kind of move through this to get through it by the end of the hour and have you understand it. Okay, but here's some thoughts. First of all, if this was in a circle, see how if you kind of extend this out, you can picture a circle going around like this. That was an awful circle, but anyway, where that would be like the radius. Do you see that those two lines would be equal in length then? Okay, and so those two are both radiuses, or radii. And then this, on the outside here, this little piece right here, that would be an arc. Okay, and you're going to learn about those again tomorrow, or in this case, it's Monday. All right, this angle right here is called a something angle. I just said it last slide. Central angle. All right. Moving on. This is the meat of the stuff that you have to know for today. So you might want to take some notes on this one. All right, so this is fractions of degrees. What if you want to go 37 but a little bit more degrees? Can't you just say like 37.5? Yes, you can. But there is another way to do it that is commonly used. For instance, you have something just like this in latitude and longitude. You ever heard of like going 62 degrees 4 minutes? Know what I'm talking about? And then a certain number of seconds. All right. So the symbol for degrees is that little thingy. The symbol for minutes is that little thingy. And the symbol for seconds is that. So this is 37 degrees, 42 what? Minutes, and 17 what? Seconds. All right, I want you to think about that in terms of a time. That's sort of like saying 37 hours, 42 minutes, and 17 seconds. Do you see what I'm saying? They're getting to be smaller and smaller and smaller amounts that you'd move, so to speak. That's in time. This is in degrees, which is a little bit different. All right, so you could also write it as a decimal. And this is equal to this. 37 degrees, 42 minutes, and 17 seconds converts to that decimal. It's my job to show you how. Now, last hour I had them try to figure it out themselves, and only one kid was able to figure it out. So, and it took about 10 minutes. So I don't think I want to do that this time because it was too much pain and suffering for one kid to have a breakthrough. So I'm going to kind of get right to the point on this one. If I wanted to convert this to this, would you please write this down on your notes? Write the beginning answer, write the end answer, and then show yourself how to do it, because that's the main thing you got to learn today. All right. Where do you think I get the 37 from? Gee, I wonder. It's because it says 37 right there. So basically, the beginning of the problem, you don't even have to work on because it already is a 37. So then really what it boils down to is making that turn into that, right? Okay, so how do you get 42 minutes? Remember, it's a lot like time. Changed into 0.7047. And I'm going to tell you that the 42 minutes part gives us 0.7. How do you think I'm changing 42 into 0.7? I bet if I break it up into a little bite there. Yes? Yes. You just divide it by 60. Because this is in minutes, and I want to change it into, it's almost like I'm changing it into hours, you know, except I'm changing it into degrees. So I divide by 60. All right. So if I take that and divide by 60, I get the 0.7 part. Well, then that leaves that I've already done the 42 now. It's done. I've already did the 37. It's done its job. I'm left with that 17 seconds thing, and I bet somebody can make the leap now. Exactly. Because how many seconds are there in an hour? Remember, this is a lot like an hour. Okay. All right. 3,600. And so I take the 17 divided by the 3,600, and I get 0.0047. Uh-oh. No, I think it's 2. So the 37 is still a 37. And then I add the 0.7. And then I add the 0.0047. And the grand total comes out to 37.7. And the 0047, there'd be like a 0 here. 047. If you don't believe me, take 37, add 0.7 to it, and then add 0.0047 to it. Okay. All right. So there's a very typical problem for today. That is the beginning of a problem. That's just changing something that was written in this format, 37 degrees, 42 minutes, 17 seconds, into this format, 37.7047 degrees. If you were going to type it in on a GPS unit, I bet you that it would be easier to type 37.7047. I'm guessing not many people have their decimals nowadays with minutes and seconds. All right. So let's actually do one of these things. 28 minutes, sorry, degrees, 13 minutes and 4 seconds. Would you please change that over to a big old decimal? Definitely use your calculator. Need a calculator? Can I borrow one? I've got one. Got a calculator back here in the back row? Good. All right. So tell me, do I have to do anything to 28? No, it's just going to be 28 point something. And how do I get the beginning of my decimal? 13 divided by 60. And would you please tell me what that comes out to be? 0.2166. Okay. And then to that I have to add a little bit more. This part. 4 over 3,600. 0, what? Add it all up. I really could have put this 28 on a separate line, but 28 plus the 0.211 is going to be the same as I have. So this is just fine. 28 point, and that's going to be 2, 1, and then the 6 and the 1 makes 7, 7. Do you see how that's going to work? Raise your hand if you had 28.217 repeating. Okay, good. So that's showing it to you broken into little parts. Do you get how these are like minutes because they're out of 60? Do you get how these are like seconds? There's 3,600 of them in an hour. Well, these are not in an hour. This is in a degree. All right. So now, the next part. You'll need to understand this for some of your word problems that you'll do eventually. Today don't have any, but eventually. Okay. If I was the skipper of the boat and I said plot a course and go 23 degrees. If I just say 23 degrees, what do I mean? Well, how about this? If I had said go 0 degrees, what do you think that means? Straight what? north. Okay. And if I said, and this is traveled, measured clockwise from the due north. So if I had said, go 180 degrees, you ever heard about doing a 180? Okay, that would be like exactly, plot a course of 180 degrees would mean go exactly backwards from where you are right now. Okay. Or head exactly straight south. All right. We'll talk more about this later because it doesn't affect us really much today. I just want to mention it since it's in here. And the next part, this is important because we're going to be converting between radians and degrees. Do you even know what a radian is? Do you have any idea? Yes? Okay, have you heard of a radian before? All right. Would you grab your calculator, please? Hit the mode button. Do you see it? Is it the second thing on the list? Third thing on the list? Okay. Third thing on the list is a choice between degrees and radians. Leave it in degrees for right now. Okay? Because that's what you're used to. But radians is another way to measure something. It's sort of like this. Okay? And if it's in radians, switch it to degrees. All right. It sort of should default to that. Now, let me give you a best example of what measuring in radians versus measuring in degrees is kind of like. It's sort of like saying in the United States, I might say that I weighed 220 pounds. But if I was in some countries, they actually could give me a weight in stones. You know what I'm talking about? I can't remember which country it is. I think it's in England. Yeah. And if so I said I was, 23 stones. That's actually a way to measure you. Okay. Every stone is a certain number of pounds, so to speak, and so they would completely understand. Somebody that was used to that system would be like, oh yeah, I know what that means. Okay. Horses. Did you know that you can measure a horse in hands? You heard of that before? Instead of saying that the horse was 178 centimeters tall, or however tall he was at the shoulder, okay, you could instead say how many hands tall he was. Okay, that's a measurement. It's just a different way to measure. Horse is the same. I can say he's 178 centimeters, or I could say he's like 52 hands tall, or whatever. That's ridiculously high, but anyway. So, radians and degrees are just two different ways to measure the same thing. You got one angle. Oh, by the way, a hand is measured from the side, in case you're wondering. It's from the bottom of your hand to the top, like where I don't think it includes the thumb. All right, anyway. So, and that way you can just stand there and like put your hand on the ground and like actually measure it yourself on a horse. You could say, oh, my horse is like 23 and a half hands or whatever. Yes? Go ahead. All right, so this is radians versus degrees. You need to know this picture. Right here. This is A. This is A. And that only makes sense that they're both A. Because if this is really a circle, they're both radii, right? You get that? The last part is what makes this a radian right here. And that's if this distance is also A. If this arc length right there, that length, remember it's a curving line, so it's trickier to measure. That arc length is also A. If these are all A, and that's a radian. About how many degrees is it? It's in the neighborhood of 60. Okay, I'll have you figure it out exactly in just a minute, but a radian's about 60 degrees. It's just a different way to measure an angle. Instead of measuring it in degrees, you can measure it in radians. All right, so if I had this angle, it was about like that, I could say it's about 70 degrees or like 1.2 radians. Usually they don't use a decimal. They might do like 5 over 4 radians. All right. So it's just a way to measure an angle. All right, moving on. So how many radians are there in 60 degrees? Well, there's a complicated system that you can use to like prove how you change radians to degrees, but I need you to just know this for today because it'll kind of, again, cut through it pretty quick. You need to know this formula, that if you want to convert radians to degrees, you got to multiply by that. If you want to convert degrees to radians, you can multiply by that. Would you please write those two things down? It'll help you to remember them. Two important factors you need to know. 180 over pi radians, and that's not just 180 over the number pi. You got to understand it's 180 degrees over pi radians. It's a factor. It's a lot like 1 foot over 12 inches. Sort of like that. All right. So if I have radians and I want degrees, I can multiply by this one. Now, I know you're going to forget which one goes with which one. So you need to be able to make logical sense when you're doing it. So what you can't afford to forget is that there's 180 involved and that there's a pi involved. Okay? And at the 180 is degrees. All right, so if it's 180 degrees and a pi, see if you can figure out if I've got, let's say, 2 radians, and I want to change that into degrees, then just a second ago, at the beginning of the hour, we were talking about changing like feet into feet into miles, or miles into feet, okay, or seconds, hours into seconds, that kind of thing. And we were multiplying by a factor here. All right, we have to multiply like that. Do you think we should multiply by the 180 degrees over the pi radians, or do you think we should multiply by the pi radians over the 180 degrees? It's got to be one or the other. 180 degrees over the pi radians. Because why? You want radians to cancel? Exactly. That's the way you should think, is what do I want to cancel? I want that to cancel. And now I'll be left with degrees. And that's what I wanted. So you take 2 times the 180, you divide it by pi, and you'll have your answer. You get like 114-ish? That sounds right. Degrees. So 2 radians is about 114 degrees. Let's actually do the same exact thing for 1 radian, because I told you a second ago we'd figure out exactly what 1 radian is. Write this on your paper. This is a big one you might want to star. So 1 radian is equal to, well, I'll figure it out in a second here. So what are you going to multiply by? 180 degrees over pi radians. Does that sound right? Now the radians will cancel. Doing, doing. And what do I have left? 180 divided by pi, which is? So when I said it was around 60, was that right? Kind of close. A little less than 60. So a radian is around 60 degrees. In fact, it's exactly that many degrees. Okay, so how about if it goes the other way? What if we have something that's 29 degrees and we need to know how many radians it is? So now you just use the same exact fact except flip it. So now you do 180 on the bottom because you want the degrees to cancel, and then you do pi radians on the top. Cancels, cancels. 29 times pi divided by 180, and you'll have your answer. What is it, by the way? Somebody with fast fingers. Yes? You got it? Anybody verify that? Something? Okay, good. All right. And that's, oh, I should really write this. Radians. Okay. So you can change degrees to radians that way. Now, to put it all together, you have to be able to do a problem like this, where they give you something in DMS. What do you think that means? Degrees, minutes, seconds. Good. Like this. And then they want that converted into radians. First, convert it to degrees in decimals. Then, you just do that second thing that we did. So I taught you two processes. The first one was changing something in degrees, minutes, seconds into a decimal. So that's 61. And then this part, what do I do with that again? 24 divided by 60. Somebody do it quick. What's 24 divided by 60? So you take the 61 and you add that, and you get 61 point what? And that means I got 61.4 degrees. Now I'm ready to convert it to radians. So I multiply by that thing. And where should I put the degrees so that they'll cancel? On the bottom. So I put the 180 on the bottom and the pi radians on the top. And then that'll cancel that. And that's so I can take 61.4 times the pi and divide it by 180. Okay? All right. So what I want you to have learned so far is a bunch of stuff that you used to know about sine, cosine, tangent. A little bit about those triangles, the 30, 60, 90, and the 45, 45. I want you to know that degrees are a way to measure these angles, but there's also what? Radians. About how big is a radian? Around 60 is a little less. And then if you wanted to know exactly what two numbers are involved with that, 180 and pi, and it's in degrees and radians, yes. Okay, so if you had to convert something in degrees, minutes, seconds, like 28 degrees, 14 minutes, 5 seconds, you'd take the 28, you'd add 14, what's 60ths, and then you'd add, what, 5 3600ths. And then I'd have my grand total of 28 point something. And then I could use that decimal if I wanted to change it over from degrees to radians if I wanted to. That's all you need to know for today. You made it through Friday.